Okay. So yesterday we were discussing about vector spaces. Okay. And we also introduced the concept of dual space. Okay. And we are interested in how the component of vectors, okay, transformed when we change the basis. Okay. So I think, but in the last part, I should be more careful because it is important. So I will again repeat the last part of our previous lecture. Okay. So recall. So we have a vector space V, okay, and let small v be a element of this vector space V. Okay. If I provide a basis set B to this vector space, okay, I runs from 1 to dimension of the vector space, okay, then I can express this vector V as a linear combination of EIs, okay, and I will write this component index of this component as superscript. Okay, the reason will be clear later on. Okay, and I will write this vector. So I can express any vector as a linear combination of this basis. Similarly, corresponding to this V, okay, I have a dual space which is denoted by V star, and let V tilde be the element in this V star. Okay, given the basis in V, that is B, okay, one can construct basis B star in V star, okay, and which I am denoting by basis vector but subscript I. Note that for expressing basis for a vector space, I am using index as a subscript. To express basis in dual space, I am using index as a superscript. While on the components, okay, to express a vector as a linear combination of basis vector, I am writing this index or component as superscript. Okay. So now this is the basis for dual space. That means any vector, say v tilde, okay, can be written as a linear combination of this basis for v star, that is this b star. Okay, and the components of v tilde I will write as a subscript I, ei. Okay, note that I am not writing tilde here. Okay, because see, I can distinguish why I'm writing tilde here, because this vector is in general different than this dual vector. Okay, but while in components, okay, I have anyway denoted this vector components by superscript and dual vector components by subscript. Okay, so they are different. Okay, so I don't need to write tilde here. Okay, vi's are different than v lower i's are different than v upper i's. Okay, so this is the specification of a given vector in vector space and given vector in dual space. Okay, and note that how we constructed this dual basis. Dual basis is constructed in such a way that we define the map such that ei ej is delta ij. Okay, it does not mean that this basis is orthogonal to this basis. Okay, it is the definition, it is the way we define this map. Okay, remember, these are this e upper i's are elements of dual space. That means they are linear functionals. Okay, so they eat the vector and gives us a scalar. Okay, so for a given value of I and j, we will get corresponding numbers here. Okay, it does not mean that this basis e lower i's and basis e upper i's are orthogonal. Okay, because they lie in different vector spaces, so there is no uh, reason, there is no way to define orthogonality between these vectors because they lie in completely different vector spaces. Okay, so now the question is, Suppose if I supply another basis, so I have vector space V, I have basis B, and I supply another basis B prime, okay, for this vector space. So B prime is E prime I, okay. Under this, so we have basis B and we have basis B prime, okay. Now the question is how the components of vector look like, a component of vector V look like in this basis and in this basis. We know how component of vector look like in basis B, that is V upper I, okay. Given this, the question now is how the component of this vector look like in this basis, okay, fine, okay. So first I will change the notation from our yesterday's notation, okay. So this basis vector ei prime, okay, I will write, since these basis vectors are the elements of V, I can express them as a linear combination of these ei's, okay. So that linear combination, instead of writing prime here, okay, let me write, okay, so let me write by definition, okay, I will denote this E prime I as EI. Instead of writing prime on E, I will write prime on this index. It does not matter, right? This is a primed index. It denotes that we are in the primed frame. Okay. This is equal to some linear combination of these EIs. Okay. How I will write that linear combination? I will write some numbers A, J, I prime and EJ, and summation over J is implied. Okay. Fine. Okay, so ei prime, that means the basis vector in prime frame, is equal to summation over j ai prime upper j ej. Note the placement of these indices. Okay, I am summing over j.
Sir,
Okay. Yes.
sir, you said that the question is infinite, means J is infinite, right?
No, 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 no. J, why j is infinite? It is a finite
Yeah,
number. It's a finite dimensional
yeah,
number.
yes, yes,
Okay. Okay. So
yes,
summation
sir.
over j ai prime j ej. Okay. Fine. Okay. Now given this, how the components in components of vector v in this frame will look like. Okay. So now I will write vector v as summation over I. Okay. Vi ei. I will not write caps now. Okay. It's understood that these are bases. Okay. Is equal to, I am looking at the same vector but in different bases. Summation over I. Okay. Vi prime, okay, ei prime, okay, fine, okay. But this is equal to, now you substitute the relation for ei prime in terms of unprimes, okay. So this is equal to summation over I vi prime, okay, and ei prime is summation over j, okay, a I prime j is a, okay. But note that this is the summation, this I index is summed over. So instead of I can use this, I can use here J index. So V equal to summation over J, Vj Ej, okay, is equal to, so I will write first J summation over J, okay. Then I will put bracket summation over I, V I prime, okay, and a j I prime, okay, and I will write ej, okay. Because these are basis vector, I can equate the coefficients, okay. Hence I will get vj equal to summation over I, okay, v I prime, okay, a j I prime, okay. So this is how the components in two frames relate to each other. Okay, this implies that, Okay, so I want to write vi prime in terms of unprimes. Okay, so first let me write okay. So first let me write this in the matrix notation. Look at this equation. Okay, here in this relation the summation is over j. Okay, in this relation the summation is over I prime. Okay, is it clear? That is the important difference. Okay, so how I can write this in this matrix notation? So v, okay, component of v in B frame is related to component of v in B prime frame in the following way. Okay, so it is A, okay, and component of v hmm, in B prime frame. Okay, clear? I will, this is matrix A. I will explain what this matrix is. Okay, this is a matrix formed out of these coefficients. Okay, this implies that the component in prime frame, this is the column vector, okay, is equal to A. Okay, so let me write here A inverse. Okay, I will explain later on what is this A is. A inverse, then this is A and component of V in B basis. Okay, clear? Okay, so we have, now we have to figure out what this matrix is. Okay, so this I'm writing A inverse. See, I could have written here A, then here it will become A inverse. Okay, it's up to us what to call A and what to call A inverse. I'm denoting matrix formed by this as A inverse. Then the relation between primed component and unprimed component is prime component equal to A times matrix multiplication with VB, V in basis B. Okay, is it clear? Okay, so now we have to figure out what this matrix is. Okay, this matrix A is, okay, this matrix A is, just a minute. Okay, it is A 1 prime 1, A 1 prime 2, and so on, A 1 prime n, okay, then A 2 prime 1, and so on, and so on. Here A n prime 1, here it is A n prime n. This is the matrix. Okay, look at the way we define the matrix. The primed indices are coming upstairs. Okay, the primed indices are coming upstairs. Okay, but here in last expression, okay, in the last expression, we had the summation over primed indices, but here it is coming downstairs. Okay, is it clear? Okay, how this AJI prime, okay, and AI prime J are related. Okay, they are basically the inverses of each other. Okay, they are basically the inverse. This AJI prime is inverse of AI prime J. Okay, clear? So note that where I am summing, okay, that is important. Okay, normally when you write the column vector, okay, and there is a 3 cross 3 matrix and again 3 cross 3 column vector. Okay, when you multiply, okay, this is denoted by Aij xj, and these are the columns. So column index is summed over. So xi, okay, here it will be x1, x2, xn. Okay, so xi equal to aij xj. So it is x1 equal to a11 prime. Okay, it is a prime sum. Okay, so x1 prime equal to a11 x1 plus a12 x2 and so on. So it is the column index which is summed over. Okay, that gives you the correct matrix multiplication rule. Okay, so we also want the same thing here. Okay, so here the column indices should be summed over. Okay, is it clear? Okay, here the column indices should be summed over. Okay, so this denote this this is what is happening here. This column indices, okay, this okay. So if I make a convention that this is my, okay, so I will go to next page. It will be better. Okay. Okay. So here a I prime j. Okay.
Sir,
This is just a minute. This is my row index, and this is my column index. Okay, clear? So lower one, okay, they are columns. Okay, 1, 2. So the column is changing here. And these upper ones denote row. So row is changing here. This is my convention to define matrix A. With this convention, we need to set this. Okay. I could have chosen otherwise also. It will not create any difference. Okay. But later on, the present convention is helpful. Okay. Fine. Okay. But I need to explain this. Oh, yes, there was a question.
sir, it's not about the question. Sir, can you change the color of the cursor, the pointer? Can you make it dark or some other color? Because it is sometimes due
No,
to the
no, that I
blurring,
cannot
it
do.
is unable
That I
to.
cannot. That I
Okay,
cannot do. Okay. Okay.
okay, thank you.
So because this is inbuilt, that I cannot do. I think, yeah, I cannot change the color of this cursor. Okay. So this choosing A or choosing A inverse is the convention, but this is not the convention. This is what it's coming. So if you assume basis transform like this, then the column transforms like this. This is not about convention. This is what we get. Okay, but now you see, consider this equation. Let me consider this equation. Let me rewrite this expression. Okay. Yes, I should not. I should this trash. Okay. So let me write the previous equation. Vj equal to v prime I aj I prime summation over I, summation over I v I prime aj I prime. Okay, fine. To get this, I need to multiply by inverse. Okay, so suppose if I multiply from the left, sorry, from the yeah, so I will write this, instead of writing this, I will write this vi prime here. There is no difference because these are just numbers. I can write this here. Okay, to get this vi prime in terms of v's, okay, I have to multiply by inverse from the left. Okay, so I will multiply a inverse a inverse I some, okay, let me write I prime j, I prime j, okay, vj summation over j equal to, okay, so now I have to use here different index, so I will use k. Okay, a inverse I prime j, okay, a j I prime, okay, V I prime. Okay, since I am multiplying by inverse, these are the, by definition, this is my inverse of this, inverse element of this. So this will be summation over k, very here should be k, sorry, k prime, then there should be k prime. Okay, summation over k, this is by definition a inverse a is this, j is sorry, here j is also summed over. Okay, so I had to summation, make the summation over j also, not j. Okay, there's some mistake is here, there's something is wrong here. uh, a inverse j, this is correct, j summation over j, summation over, yeah, I think I missed something. Mm, summation, I need to multiply by a inverse. Okay, a inverse I prime j summation over j equal to a inverse I prime j summation over j should be there. Okay, so it is, there should be summation over j because I am taking the summation over j. Okay, so summation over j here. Okay, k delta summation over j a inverse I prime j. Okay, a j k prime is nothing but delta I prime k. It's like I'm using this I a I j a inverse j k is delta I k. Okay, this is what I'm using. Okay, here. Okay, so it is delta. So summation over j will go now. And I will left with delta I prime k prime. Okay, v k prime, that is equal to v I prime. Okay, hence we have v I prime equal to summation over j. Okay, a inverse I prime j vj. Okay, so this is what the inversion of this relation. Okay, this relation. Okay, now we will choose the convention. Instead of calling this as a inverse, I will call this as a. Okay, then this will become a inverse. Okay, hence, so okay, I will write this as, by convention we will choose the convention in such a way that this I will call as a. Okay, so v I prime equal to summation over j. Okay, a I prime j vj. Okay, clear? And in the matrix notation, this becomes component of v in basis b prime equal to matrix A and component of v in basis b. Okay, so the moment you do A, it means this our original function, here it is a prime. Okay, so this is the inverse of default. Okay, is it clear? Okay, now I will write my matrix. Okay, then inverse will be a 1 prime, a 2 prime. Remember, is column. A 1 prime, a 1 2 prime, a 1 3 prime, so on, n prime, then a 1 prime, I n 1 prime, a n prime. Okay, compare this with matrix C. What's happening? To delete this page. Okay. So you compare this matrix. Where is that matrix? So A11, A1 prime to A1 prime n. Lower, okay, upper row.
Excuse me, sir.
Primed index. Yeah.
I think we are experiencing audio lag.
Are you experiencing audio loss?
Yeah, so the screen is not visible to me.
Yes, sir, your audio is lagging.
Yes, sir. Audio is lagging.
Just a minute. So, strong enough. I don't know. So yeah, I will go slow in the long time. So matrix A prime index is coming upstairs. These are rows, and unprime index are coming downstairs. These are columns. Okay, the unprime index, the low unprime index is column or column index matrix. Okay, and inverse your primed index is coming down. These represents column index. Okay. So we have in this notation we have a I prime c, a I prime j, a j k prime. Okay, is equal to delta prime prime. This is basically inverse element of this. Okay. Is it so? For example, if I have a1 prime 2, okay, then what come here? So I will get 1, number 1. Okay. So I should write a2
So,
1 time. Okay.
hello?
Yes.
So your voice is breaking or not?
Yes, sir.
Maybe I will rejoin. Maybe I will stop it and I will rejoin. Maybe. Let us see. Hello.
Yes, sir.
Yes, sir.
Now is it okay? The
Uh,
there is no lag, right?
No, sir.
no, sir, it doesn't seem so.
Okay, fine. So the so what was the last equation you heard correctly?
Sir, actually, this new slide wasn't visible to us. The frame got freezed on the last slide.
Okay.
Yes, we couldn't see you writing all this new thing on new slide.
Okay. So now this is visible. This thing, this
Yes,
slide.
now it is visible. A inverse matrix.
Yeah. So A inverse is this. Okay. So A I prime J, A J K prime is delta I prime K prime. Okay. So suppose if I want inverse element of A1 prime 2, then it would be A2 1 prime, right? Okay. That will give me 1. Okay. And so on. So these are the inverse elements of our matrix A. Okay. Is it clear? Okay. So we have the transformation of components. We know how components transform. Okay, and they transform in exactly in the opposite way of the basis. If the basis transform in one way, then the corresponding component transform in another way. Okay. So now the question is, next question is how. Next question is, given the change of basis in phi, okay, how it affects on the components of a dual vector. Okay, this is the question. Now we have to find how the dual component transform under the change of basis made in V. Okay, is it clear? Okay, that is the question. Now let us do that. Okay, we will use the defining relation for dual space. Okay, so what is the defining relation for basis in dual space? EI EJ is delta Ij. Okay, fine. This will be used. Okay, now let us consider the vector V, any dual vector V tilde, okay, belongs to V star. Okay, this I will write as Vi EI. Okay, summation over I. I can write as a linear combination of dual basis. Okay, I want to see how this component changes if I change the basis in V. Okay, so how I'm going to do? Okay, this, okay, just a minute. Okay, yeah. So firstly, in order to know this, we should know how this basis transform. Okay, if I change the basis in V. Okay, how this do? First we should know how the dual basis changes if I change the basis in V. Okay, that is very easy to get. Okay, so we will use this relation. Okay, so this will be, suppose my basis B star changes to B prime star. Okay, which is E I prime. Okay, so in our new notation, it will be E I prime. Okay, so this is my new basis, and my old basis was E I. Now we are in dual space. Okay, so now let us consider action of E I prime on E j. Okay, old basis in V. Okay, this will be equal to, okay, this is equal to E I prime. Now tell me, how should I write E j in terms of E prime j or E j prime? This E j I want to write as a primed basis. Okay, so this will be achieved by using these transformations. Okay, these transformations. So you go back here. Okay, you consider this. Okay, if this is my change of basis, then what will be EJ? EJ will be EJ will be A J I prime. Okay, E I prime, right? Okay, correct. Okay, so I will use this here. I will substitute it here. Okay, so I want EJ. So EJ will be A J I prime. Okay, but I prime I have already used. Okay, so let me use some different index, because that index will be summed over, right? This I prime, whatever it comes here, it will be summed over. So let me use K prime. Okay, and then E K prime. Okay, but these are linear functionals. So, and these are A K prime J's are numbers. Okay, so remember, there is a summation over K prime. Okay, here there is a summation over K. Okay, so this is equal to summation over K. E I prime will act on this. Okay, so I will take out A K prime J. Okay, and E I prime E K prime. Now our new basis, whatever that basis may be, will be such that if I act new basis vector on new, sorry, if I consider any element from new dual basis, these are dual basis. Okay, this one is old dual basis and this one is new dual basis. Now suppose if I consider any element in this new dual basis, and if I act on new basis in V, I must get delta, right? So this is equal to summation over K, okay, A K prime J, and this will be delta I prime K prime. Okay, fine. So this is equal to, so we have the relation E I prime acting on EJ will be equal to, if I use delta, okay, it will be A I prime J. Okay, what does it mean? Action of new dual basis on old basis is A I prime J. Okay, is it clear? Okay, now you come to this. Okay, if this is the relation, if this is the action of new dual basis vector on old basis vector, okay, then you consider the following. Okay, now you consider the following. Okay, you consider any dual vector, write it in terms of old dual basis. In old dual basis, its components are denoted by V lower I and EI. Okay, this I am considering the same dual vector, so this must be equal to summation or I V lower I prime E upper I prime. Okay, clear? So this is equal to, now you can substitute. Okay, now what is our aim? Our aim is to calculate this. Okay, fine. Okay, so either we can substitute the form of ei here or form of ei prime here. Okay, both are same. Okay, so let me substitute the form of ei prime, ei here. Okay, so this is equal to, this is nothing but summation or I vi. I will use ei. Okay, ei will be a I prime. So what was our result? Previous result. Okay, so ei prime ej equal to a I prime j. That was our result. Okay, then what is the relationship between, from here we can easily get the relationship between e I prime and e I. Okay, what will be the relation? Can anyone tell me what will be the relation between these? From this, just tell me the relation between ei prime and ei. What will be the relation? This is equal to, okay, ei prime will be equal to a I prime, okay, j is a. This will be the relation. You can just convince yourself, just use this. Okay, use the definition of ei. Okay, and you will get this immediately. Okay, why this should be the case? You consider ei prime and act on ej. Okay, so suppose if this is true, okay, let me go to this. Okay, suppose my claim is e I prime equal to a I prime j ej. Okay, my claim is this is correct relation. Why this is correct? Because if I act ei prime on, say, ej, that is original basis vector, old, okay, then it will be a I prime j. Okay, sorry, let me act on ek. Okay, then a I prime j e j acting on ek. Okay, but this is just delta jk. Okay, so it will be a I prime k. Okay, and this is what we, so e I prime acting on ek is delta I prime k, and this is consistent with this. Okay, e I prime ej is delta I prime j. So e I prime ek equal to a I prime k, and this is what we are getting here. Okay, okay, so this is my correct relation. Okay, so now you substitute this here, or you substitute, either you substitute for ei or you substitute for ei prime. Okay, let us substitute for ei prime. What we are going to get? Okay, if I substitute, yeah, so if I, it will be better if we substitute for ei. Okay, so ei will be inverse of this. What is the inverse of this? Inverse of this will be a I some index k prime, okay, e k prime. Okay, this is equal to summation over I v I prime e I prime. Okay, but now you see, I can write here, this is summation over k here. Okay, so summation over k I can write first. Okay, then I will write vi a I k prime summation over I, okay, and e k prime is equal to, this I prime is summed over index, so I can write here k prime, sorry, not in summation, there is no prime here, k v k prime e k prime. Okay, now you compare the coefficients. Okay, this implies that v k prime is equal to v I a I k prime. Okay, is it clear? Okay, so this is how your component of your dual vector will transform. Okay, this is the component in basis b star, and this is the component in basis b prime star. Is it clear? Okay, now I want to write this in the matrix language. What will be this expression in the matrix language? Okay, remember this is the summation or what? Okay, now you go back to our matrix notation. Okay, go back to this matrix notation. Okay, A is defined as upper primed index. Okay, then A inverse will be defined as lower primed index. Okay, clear? Okay. So now whatever is coming here is inverse, right? So this means that component of V dual vector, okay, in I will write that B tilde now. Component of dual vector in basis B prime star is equal to, what should I write? You tell me now. What should I write? Note that the sum where I am summing, this upper index is summed over. Okay. Recall what was our A inverse? A inverse was A 1 1 prime, A 1 2 prime, A 1 3 prime, and so on. Then A 2 1 prime, and so on. Now with this, tell me how should I write this in the matrix equation? What type of matrix should I write? This in this notation, what are the what is the column index? This 1 prime, 2 prime, 3 prime, they are column index. That means this k prime is the column index, right? Then this I will be row index, and I am summing over I. So row is summed over. Okay, then what should I write here? If it had been like this, okay, suppose if it had been like A I k prime V k prime, right? Okay, then this would be just this would mean A inverse V B. Okay, but now I am having summation over I here. What does it mean? What should I write here then? Any thought? It means, see, my row index is summing, is summed over. Okay, to change it to column, what should I do?
Transpose.
Yeah, so it will be
Inverse.
A inverse transpose here, right? Correct? Okay, so this is the correct expression. Is it clear? Okay, because you should notice that how where this I index where this index is summed over. This sum is over row. Okay, so it means that if I take transpose, then I will get summation over columns. Okay, then in fact this will be written as A inverse transpose, and then you sum. Okay, you this index, this element is the element of A inverse transpose. Then only then I can do this multiplication. Is it clear? Or if you are in doubt, then you can just explicitly write all the, you consider one example and you would explicitly you will get this appropriately. Okay, but I'm not doing any example. Okay, But if you are doing one, it will be better if you do one example. Okay, in that example it will be clear. Maybe I will do one example just to illustrate. Okay, just to emphasize how this A inverse transpose is coming. Okay, so in summary, what we have, okay, to summarize these results, okay, what we have, okay, we have under the change of basis, okay, the basis in your original space will be transformed like this. Okay, then components of a vector in your vector space will transform according to this relation. Okay, so this is for V. Okay, then your basis, given this change of basis in V, okay, the basis, your dual basis will transform according to this relation. Okay, and your component of dual vector will transform according to the following. Okay, you see now the way basis transform, okay, component of dual vector transform in same way. So these and these transform in same way, right? Because aj I prime, aj I prime, correct? See the connection. The way your original basis transform, your component of dual vector transform in same way. Okay, and the way your dual basis transform, your component of vector transform in that way. You understand? Okay, so component of dual vector transform in same way as the basis in V. Okay, and component of vector transform in the same way as the basis, as the dual basis, as the dual basis. But note that the change in dual basis is induced by change in basis in V. Given the basis in V, we are constructing dual basis. So if I change the basis in V, obviously I need to change dual basis. Is it clear? Hence the name, hence we say that these components, okay, the component of a vector are contra. Contra means in contra, the transformation of basis and transformation of corresponding vector, they are in opposite. Okay, so you have a vector, okay, these are the component of vector and this is the change in basis. So if basis transform in one way, then the component transform in opposite way. So relative to this change of basis, okay, these are called contravariant component of a vector, and this is covariant in the sense that the component of dual vector transform in same way as your basis. So this nomenclature is relative to this change of basis. Okay, if you say that I will denote this as my change of basis, then accordingly we need to change the co and contra. These are nomenclatures. Okay, contra comes because of the way vector component transform relative to change of basis. They are in opposite way. On the other hand, your dual vector component transform in same way. Okay, but this is not the only difference. There will be certain other features of these vectors. Okay, but this is the important part. This you should know by heart. Okay, if I change the basis in vector space, your component will transform in opposite sense. Your dual vector transform in opposite sense of your dual basis will transform in opposite sense of your original basis, and hence the component of dual vector transform in same way as your original basis. Note that the basis and the component of a vector, they transform in such a way that that vector, say v, remains same. Okay, so basis transform in one way and your component transform in another other way, so that this v remains same, fixed. And that should be the case, right? Because if I have 2D space and if I consider any vector from P to Q, okay, so whether you look at this vector in this frame or you look at this vector in this frame, okay, vector A, suppose if I call this as vector A, which points from P to Q, that remains fixed, right? Whether you are in this frame or whether you are in this frame, the vector A will always directed from P and end towards Q. That is not going to change if I change the frame. So your vector remains fixed, okay, but components and the basis in which you are representing these vectors, they must change. This way of seeing the vector, okay, this way of transforming the component of vector is called passive transformations. Okay, okay, where I'm keeping my vector same and I'm changing my basis. Okay, but the same physical result, okay, suppose if you attach some physics to it, then the same physical result can be obtained by actually changing the vector. Suppose if I have a vector PQ here, vector A here, for simplicity, I am considering that vector originating from the origin. Anyway, you can take this vector, parallel transport it and attach to origin. That is not new to you. Okay, so you consider this vector and change the basis and do as we did all this process and you see the components. Okay, or you can change, suppose you change the basis like this. Okay, so this is your E1, this is your E2. Okay, then you change the basis and you have E2 prime and E1 prime. Okay, so this is change of basis. Now the same physical result can be obtained by doing the following. You keep this basis fixed, but you change this vector in opposite sense. Okay, this is A and this is A prime. Okay, so in second you are actually changing the vector. Okay, in first one your vector is same but your basis has been changed. This way of looking at the transformation is called active transformation. I, I think you must have seen this before, right? Am I correct? In quantum mechanics or in classical mechanics, you must have seen this before. Okay, fine. Okay. So is this clear? Is this crystal clear, or should I do one example? If it is not clear, then ask, because everything will depend
Yes,
on
sir.
this.
Example, please.
Pardon?
Please take an example, sir.
Just take an example, sir.
Okay, so what example? Let me find one example of this. Okay, so let us consider. Okay. Okay, fine. So let us consider example in R2. Okay, let us consider example in R2. Okay, let V be your R2. Two-dimensional real vector space. Okay, and consider our previous problem. Okay, let us consider this coordinate system. Okay, label it with the basis vector I will choose as E1 and E2. Okay, so my basis is E1, okay, and E2. Okay, so what will be this basis? You know now vector spaces. Okay, what will be this basis? Suppose if I call these as standard basis, then what will be this? This will be 1 0 and this will be 0 1. You know this, right? This is standard basis. Okay, so standard basis for R2 is consist of 1 0 and 0 1. One of them I'm calling as E1 and one of them and other one I'm calling as E2. Okay, so these are my basis vectors. Agree? Okay, and let us consider, for example, the position vector R. Okay, let us consider the position vector R. Okay, in fact, just to illustrate change of basis, I don't have to consider this right now. Okay, so let me erase it. There is no role of position vector because I want to construct the transformation matrix. Okay, so now let me change this basis to this. Okay, I will make this as my E1 prime and this one as E2 prime. Okay, fine. Okay, now by looking at this geometry, okay, you can write E1 prime, okay, you can write as linear combination of E1 and E2. Okay, what linear combination of E1 and E2 you can write? Okay, suppose this angle is theta. Okay, so what linear combination you can write? Okay, E1 prime. Okay, E1 prime will be E1 cos theta plus E2 sin theta, right? It will be E1 cos theta plus E2 sin theta. Okay, this implies that coordinate of basis E1 coordinate of E1 prime in basis B. Okay, so I should write here my another basis, that is B prime, that is E1 prime and E2 prime. Okay, note that your B is standard basis 1 0 and 0 1. Okay, so your prime basis is E1 prime and E2 prime. This is your E1 and this is E2. Now what is this E1? If I want to write this, okay, like 1 0, I should provide you the angle, right? If I know the angle, then I can write it like this. Okay, but let us not do that. Okay, what will be the component of vector? See, for this basis, in this basis, E1 prime I can express as a linear combination of E1 and E2. Once I do that, then what is the coordinate of vector E1 prime? Consider this as any ordinary vector. So how you calculate the coordinate of that vector, or how you calculate the column vector corresponding to this vector? Okay, you consider right hand side and write the coefficients of basis vector E1 first, that is cos theta, and write the coefficient of basis vector of E2 as your second entry, sin theta. Okay, is it clear? Okay. So this is your coordinate of or column vector representation of your this E1 prime. Similarly, you can write E2 prime. What will be E2 prime? E2 prime is this. So if I resolve it in components, it will be minus here and it will be plus here. So it will be minus, E1 sin theta just from this geometry, okay, plus E2 cos theta. So what will be the column vector corresponding to this basis vector E2 in basis B? Will be minus sin theta and cos theta. Okay, fine. Now how should I form that matrix A? Okay, so remember our convention is denote the matrix connecting bases as inverse matrix. Okay, hence with that convention my matrix A inverse will be matrix, first write this as a column and then write this as second column. So it will be cos theta sin theta minus sin theta and cos theta. Is it clear to all? My job is to find A, okay, or A inverse. Okay, so this is my A inverse. Is this clear to all?
Yes, sir.
Okay,
Is
sir.
absolutely clear? Yeah.
Yes.
Okay. So this is my A inverse. Okay. So I have the relation E I prime equal to A I prime j EJ. Okay. Fine. So from this you can get your A11 prime. So your A, this will be your A11 prime. This will be your A12 prime. This will be your A21 prime. And this will be your A22 prime. Okay. Clear? Now see the next is to calculate the component of any vector. Okay. Now our job is to calculate component of any vector. Now for that you consider some position vector. Okay, you consider position vector. Okay, you consider the coordinate system. Okay, and you consider the position vector R. Okay, you have this E1, E2, and then you have this E1 prime and this E2 prime. Okay, fine. Suppose this angle made by the position vector to E1 is say phi. Okay, and obviously this angle between E1 and E1 prime is theta. This is what we did earlier. Okay, right? This is theta. Okay. So angle made by vector R to E1 is phi, and angle made by E1 prime to E1 is theta. Okay. So now we are interested in, first you write the vector in unprimed coordinate, that means e1 e2 basis. This is your e2 and this red is your prime. Okay, so what will be the coordinates? R cos theta e1 plus R sin theta e2, right? Okay, this is the representation of vector R in e1 e2 basis. Okay, now my job is to find component of vector, this same vector in prime basis. But first of all, you should know what is the coordinate representation of this vector R in basis B, which is e1 e2. How to know the coordinate representation? It is, you collect the coefficient of first basis vector, that is R cos theta, then you collect the coefficient of second basis vector R sin theta. So this is the coordinate representation of your R in basis B. Okay, so this implies component of R.
Sir, it should be angle phi, right? R cos phi and R sin.
Yeah, angle phi, correct. So it will be angle phi. Okay, so this implies your components of R. Okay, if I write them as R1 and R2, okay, then your R1 is equal to R cos phi and R2 is equal to R sin phi. Is it clear? Okay, now you consider this basis, red basis. Okay, now what should I do? What will be your answer for red basis? Okay, in the red basis, okay, what will be the resolution of R in terms of e1 prime and e2 prime? So R, same vector, I am writing in red basis. Okay, so it will be R cos angle between this and this, that is phi minus theta. So cos phi minus theta e1 prime plus R phi minus theta sin phi minus theta e2 prime. Okay, here because I need to take this, right? This will be the components. Clear? Okay, so what is the coordinate, what is the coordinate of R in basis B prime? Okay, coordinate of R in basis B prime is R cos phi minus theta R sin phi minus theta, right? Okay, this implies your component of R in prime basis 1 prime will be R cos phi minus theta and R2 prime will be equal to R sin phi minus theta. Okay, is it clear? Okay, but this you can write, now you consider the following. Okay, so this is your R1 prime and this is your R2 prime. Okay, therefore this R1 prime R2 prime is equal to, I can expand this cos A minus B. You can also we can do sin A minus B. Okay, so if I do that, then what I'm going to get? Okay, I can write this as cos theta minus sin theta cos theta, then R cos phi and and R sin phi. Okay, but what are these? These are nothing but your R1 and R2. So this will be equal to this cos theta minus sin theta, cos theta, R1, R2. Okay. So this is my matrix A, and you can see that this A matrix is inverse of this. Okay, so that this is your inverse of A. So we have denoted correctly. Okay, so this I obtained by direct computation, direct geometrically, right? So I resolve R in E1 prime, E2 prime system. Okay, correct. But according to our formula, what should have happened? Okay, according to our original formula, this, you see, the way I obtain is by direct explicit computation. I resolve R in unprimed basis, and then I resolve R in prime basis, and then I identified part of that component as my unprimed component, right? But if I want to get this directly by using formula which we derived, okay, what will be the formula? R1 prime must be equal to A1 prime, okay, A1 prime J Rj, right? Because I am fixing now 1. Okay, so let me write Ri prime must be equal to Ai prime J Rj, summation over J. But now you fix I equal to 1. Okay, what you will get? R1 prime equal to A1 prime J. Okay, Rj. Okay, now you summation of J is there, so it will be A1 prime 1 R1 plus A1 prime 2 R2. How you will compute A1 prime 1? For that, we will use, at least you should know the transformation of basis, or you should know transformation of component. One of them you should know. Okay, so I know the transformation of basis. Okay, so A inverse I know. So this is my A1 1 prime. So what will be A1 prime 1? Okay, so you consider this matrix and calculate its inverse. Okay, the first entry in that will be A1 prime 1. Second entry will be A1 prime 2. Okay, third entry will be A2 prime 1. Fourth entry will be A2 prime 2. Okay, so from this matrix you calculate the inverse. Okay, so A inverse inverse, so you will get A. So you have to calculate inverse of cos minus sin, sin cos. It will be cos sin minus sin cos. Okay, clear? Okay, so if you substitute that, you will get A1. So A1 prime 1, that is cos theta R1. Okay, A1 prime 2, that will be minus sign. That will be minus sign. Minus sine theta R2. So this will be your R1 prime. Similarly, R2 prime will be sine theta R1 plus cos theta R2. Okay. Hence, we have verified, we have given one example of change of basis, and under the change of basis, how the vector component transform. Okay, that we have verified by using this example. Okay, now the question is dual vectors. Okay, okay. Now dual vectors, I wanted to postpone this discussion, okay, because there will be easy way to obtain dual vector. Okay, for R2 vectors in R2. Okay, but let us see. So we have a position vector. Okay, what is the role of dual vector? So this is a vector. Okay, so it is represented by, okay, this vector is represented by column R1 R2 in the basis E1 E2. This thing is represented by a column, and this is what we use normally. Instead of R1 R2, you call it X and Y. Usually we use this column vector as my vector, but this is actually the representation of vector is an abstract quantity. Okay, so it is represented in this basis by a column vector. That is a correct statement. Okay? Vector may or may not be column vector. Okay, column vector is just one representation. Okay, now for this E1 and E2 basis, what is this E1? E1 is standard basis 1 0 and 0 1. I need to find co-basis or dual basis E1 and E2. Okay, how to find that? We have this relation, right? E I E j is equal to delta Ij. Okay, now I have represented this vector by row. Its coordinate representation will be column. So this E1 and E2, E1, E2, okay, its column representation in basis, in the same basis, in their own basis will be what? I have these vectors, then what will be their column representation? This will be just 1 0 and this will be 0 1. Okay, this is vector and this is its representation. You can use this as my vector, okay, and this is its row representation. That is also fine. Okay, but one way or another. Okay, if you use this as to represent vector, then you use this to represent its column representation or coordinate representation. Okay, so once you fix that convention, okay, once you fix that convention, okay, how you know this dual vector? What is this action? What is this natural action? Okay, suppose if I have EI, EJ, okay, if E1, its column representation is 1 0, okay, and its vector representation is row vector 1 0, then what could be your E1? So that E1 is, okay, so let us break into components. Let us see what is E1, E1. We expect this to 1, okay, it should be 1. We have to construct this E upper 1 in such a way that E1 acting on E1 will be 1 and E1 acting on E2 will be 0. Similarly, E2 acting on E1 will be 1, sorry, 0, and E2 acting on E1, sorry, E2 will be 1. So we need to construct these vectors in such a way that you will get these numbers 1 0 0 1. Okay, but now E1 is represented by, okay, so E1 as a vector is represented by row, its coordinate representation will be column. Is it clear? Okay, so what will be your, suppose if I ask you the following, okay, see here I could have used this column representations directly. Okay, then there is a natural action. It is a multiplication of row and column. Okay, fine. So these equations translate into following: coordinate representation of E1, okay, in basis say B star. The B star is the basis, so my B star is the basis E1, E2, and we need to find this basis given the basis in vector space, that is E1 and E2. Okay, so E1, the coordinate representation of E1 will be what? Okay, coordinate representation of vector E1 in basis B is column. So the coordinate representation of dual basis in basis in that in its own basis will be row, right? Okay, then I will get row into column as a number. Okay, so we need to check E1 B, E1 sorry E1 B star, E1 B, and we have to set this to 1 and find this E1 B star. Okay, let E1 B star be two numbers A and B. Okay, then A B, and what is the coordinate representation of basis vector E1? That is just column 1 0. This is 1. Okay, this implies A is equal to 1. Okay, so this is coming from first condition. Then I have second condition, E1 B star and E2 B. Okay, correct. So this must be 0. It implies that A B acting on 0 1 must be 0. This implies B equal to 0. Correct. So my coordinate representation of first basis vector, first dual basis vector in its own basis is 1 0. Correct. Okay. Similarly, the coordinate representation of second dual basis in its own coordinate representation of E2 in its own basis will be 0 1. Correct. Okay, so these are the coordinate representation of your basis vectors. Okay, so if this is the coordinate representation, then what should be your dual basis itself? This will be just column, just transpose of this. This will be just 1 0 and E2 will be 0 1. Now you understand, this is my dual basis and my basis for vector space is 1 0 and 0 1. So that E1 acting on E1 is given by, this is defined as, take E1 and multiply it with E upper 1. Okay, so this is nothing but E1 matrix multiplication with E1. So I think you should understand this. These are the abstract vectors on the left hand side. When I'm representing them in column and rows, this becomes the matrix multiplication. So this is just 1. So you do column row multiplied with column, that is just 1, and so on. Okay, so I found out the dual basis vectors. Okay, so what are these dual basis vectors? Okay, see, the point is that we are considering very simple example here. That's why the difference is not obvious. If I represent E1, let us go back, maybe here. Yeah, if I represent E1 by 1 0, then its dual vector is also 1 0, but written only in the column form. So this in fact is also dual vector. There is no difference between vector and dual vector in this case, and this also your E2. So my dual basis and dual basis, they coincide actually, because see, I am representing basis by 1 0 and dual basis by 1 0. These are same. This is just a one way of writing. Okay, actually they are same. Okay, this is the one way of representing a vector. This is, I could have represented E1 by column, and this dual basis by row. Okay, so in this case these are same. Okay, so your dual basis and basis coincide on each other, hence everything will be same. Now you do, once I say this, you can do on your own. Okay, you know A matrix. Okay, then you know the component of dual vector. Okay, so what will be your, suppose if I give you uh, suppose if I give you the position vector. hmm? Suppose if I give you the position vector R, okay, as A E1 plus B E2, okay, then its coordinate representation in basis E1 E2 will be AB. Agree? Then what will be the dual vector? What dual vector you can consider so that you will get a number when they naturally multiply? Suppose this is the dual vector. Let us consider this is my dual vector. Say R, capital R. This is my dual vector. Okay. In principle, I can choose anything here. Okay. Suppose if I choose this dual vector and we agreed that we should represent dual vector by columns. Okay. If I represent vector by row, then dual vector is represented by column. Okay. So the vector R in coordinate representation is represented by column. Dual vector capital R in its own representation is represented by some number, say C and D. Okay, and in its coordinate representation, that means you choose some basis E1, E upper 1, E upper 2. In this basis, the representation of this basis, this capital R tilde will be row C D. If these bases also turn out to be standard basis, as it was the case, okay, then the coordinate representation of capital R tilde will be CD. Okay, so action of R tilde on R is CD, is same as CD acting on AB. So it is just CA plus DB. That's it. Okay, fine. So you consider any dual vector. Okay, express that dual vector. Suppose, for example, suppose you consider this dual vector. Suppose, for example, you consider this is my position vector. Okay, so for example, you consider now this as your dual vector, R tilde vector, as say C E1 C E1 plus D E2. Okay, then in E1 E2 basis, okay, this dual vector is represented, I have interchanged this vector and tilde, is represented by a column, sorry, a row CD. Okay, if they were, if E1 E2 bases are standard basis, okay, then it is just CD. Okay, so now the R tilde 1, R tilde 1, but we agreed to denote components of dual vector by lowercase, so the subscript. So R tilde 1 will be C and R tilde 2 will be D, and so on. In particular, you can choose same vector. You can say that this vector is my dual vector. That is also fine. Okay. In particular, you can choose this dual vector to be this. Okay, this is a general. Okay, but I can choose this as AE1 plus BE2. Okay, and remember that E1 and E2, if you represent E1 and E2 by rows, okay, then E upper 1 and E upper 2 will be columns. Okay, clear? Okay. Then R tilde vector acting on R is just your usual row column multiplication. So you'll get A square plus B square. Okay, so you take that as your dual vector. Okay, no, write its component in this basis. That is, now it will, in special case, it will be E and A and B just. Okay, and you see now this is your basis. Okay, now what is, how this basis changes if I change my original basis? Okay, if my original basis is changed like this, if my original basis, where is that? If my original basis change, sorry, where is my change of basis? So this is my B prime. So if my original basis is changed like this, then what is the change in your dual basis? That you can calculate. It is given in the in terms of that A matrix. Okay, so is this clear, the example? You can do this now. You can calculate this E I prime is A I prime J E J, and use this formula V I prime equal to A J I prime V J, summation of J, here summation of J. Okay, and see how this component transform. Okay, and you will get to know that this is indeed, in the matrix notation, it will be A inverse transpose. But you see that A inverse transpose, it will not be evident in this simple case, because see, the reason is the following. Okay, what kind of matrix I am having here? What kind of matrix I am having here? What kind of matrix is this? It is orthogonal matrix, right? This A is orthogonal matrix. What do I mean by A is orthogonal? When I say A is orthogonal matrix, for orthogonal matrix, A transpose is one identity. So A inverse equal to A transpose, right? Okay. So because of this orthogonality, at the end you will get the same result. Okay. A inverse transpose is just A. You will again get A there. Is it clear? Okay. But this is one specific case. In this specific case, A inverse, we are getting orthogonal matrix. It's not general. Okay, in general, it may or may not be the case. Okay, so this is the classification of vectors, the transformations of vectors and dual vectors. Okay, so how vector component transform? V I prime equal to summation over J A I prime J Vj, and this is the takeaway message. Okay, practically you will use this only, and V I prime will be equal to summation of j a I prime j vj. Is it clear? Okay. Once you digest this, okay, next thing will be easy. Okay, we are going to call these as contravariant vectors, and these as covariant vectors. But note that the way we define this, okay, we define this, how we define these dual vectors? Through linear maps. Dual vectors are basically linear maps. Okay, dual vectors are basically a mapping from V to R. Okay, V to F. Similarly, I can say my vector V is a map from V star to F, right? Okay, so I take vector, okay, I consider a vector, and when it acts on some dual vector, say now I will write do a slightly different dual vector, say W tilde, okay, then I will get a number, or I should say in more sophisticated language, a scalar, some scalar. Similarly, when I act W tilde on V, I will also get a scalar. Right? Now, the natural question arises, can I define a map from V? I will take vector space, okay? I will take the same vector space again, okay? That means I will take Cartesian product of that two vector spaces. I will take V and Cartesian product with itself, V cross V, okay? And if I define a mapping this to F, what kind of object gives me this kind of mapping? Okay, then I can define a mapping from V star cross V star to F. What kind of objects will give me this kind of mapping? So you see, mapping from V cross V to F means I am taking two copies of vector spaces, acting some function, and I am getting a number. Here I am taking two copies of dual space corresponding to V. Okay, I will act with some object, and I am expected to get a number. Okay, on one, see, now you compare with this. I have a vector, so I have a dual vector. When I act on vector, I will get scalar. Okay, so this is the mapping from V to F. I supply vector from vector space, I get a number. Here now I supply two vectors in vector space, I will get a number. Okay, so it, in a sense, this case will be generalization of dual vector, right? And this case will be, I have two copies of dual space, I will act something, and I am expected to get a number. So this case will be generalization of vectors. Okay, there. So suppose let T be a map which takes two vectors, say v and w, and gives me a number. Okay, gives me a real number. Okay, for v, two vectors v and w belongs to capital V. Okay, so what kind of object is this? In a sense that if I now consider change of basis in V, how this object will look like in different basis. Okay, and another, suppose if I consider some t and if I act on two dual vectors, say v tilde, w tilde, I will get some number. It will be some real number. For v tilde, w tilde belongs to v star. Okay, how this transform and how this transform. So let me denote it by, say, I don't want to denote by some different name. Let me call this, no, I should not even use prime. Okay, so let me use this tilde here, and it means suppose if I have object t tilde such that if I act on these two vectors, I am getting a number, and I have object called t. When I act on v tilde, w tilde, I am getting a number. How these t and t tilde transform under the change of basis in V. Okay, so we will see that one of them will transform according to this, according to how the component of vector transform, and this will transform according to your component of dual vectors. Okay, and it will not stop here. I can define mapping from v cross v cross v to f. I can define a mapping from v star cross v star cross v star to f, and so on. Okay, so this is, I will maybe next class I will do. So this will be a tensor. This is defined as a tensor of type 02. Okay, and this will be a tensor of type 20. In this classification, your vector v, okay, will be a tensor of type 10, and dual vector will be a tensor of type 0, and so on. Okay, so tensor, when considered as a mapping, as a map, gives, it takes suppose you consider tensor of type 02. So it takes two vectors and gives me a number. So it is a mapping from v cross v, two copies of vector space, to real number. Okay, and this tensor of rank 20 will be a mapping from dual space to real number. Just compare this with this simplified case. Okay, so suppose if I supply basis. Okay, by the way, it's very half-hearted definition. Okay, so these mappings are not general mappings, they are linear. Okay, these are linear mapping, right? These are linear function. W tilde is a linear functional. V tilde is also linear functional on dual space. W tilde is a linear functional on vector space. Okay, these are also linear map, but they are linear in both V and W. So they are called bilinear. And in general, these tensors are multilinear maps. Multilinear maps from vector space or dual vector space to field over which these vector spaces are defined. Okay, so suppose if I have vector space V and let me supply basis to it, EI. Okay, clear? Then let us consider a mapping from V cross V to R. I will when I write this, it is assumed that V is a real vector space. Unless it is mentioned, this you assume that V is always a real vector space. Okay. So let T tilde be a mapping from V cross V to R. Okay. So it means that given two vectors V and W, I am getting a number. Okay. Whatever that number may be. Okay. But this T tilde is bilinear. Bilinear. What do I mean by bilinear? Okay. Firstly, bilinear means there are two slots, so it is linear in V and also linear in W. What do I mean by that? It means that suppose if I have, I will come to this. I wanted to write something, but let me first explain bilinearity. Okay. T tilde alpha V1 plus beta V2. Okay. And say alpha alpha 1 V1, beta 1 V2, and say alpha 2 W1 plus beta 2 W2 is equal to alpha 1 T tilde V1, alpha 1, alpha 2 T tilde V1 V2 plus alpha 1 beta 2 T tilde V1 W2 plus beta 1 alpha 2 T tilde V2 W1 plus alpha plus beta 1 beta 2 T tilde W1 sorry V2 W2 V2 W2. Okay, this is what do I mean by bilinearity. Okay, just to take simple case, you set alpha 2 to beta 2 to 0, so it will be like T tilde acting on alpha 1 V1 plus alpha 2 V2 and W1 say. Okay, then it will take this coefficient out and it will act on V1 W1 plus alpha 2 out and T tilde acting on V2 W1. Okay, so this is what do I mean by bilinearity. So this is a bilinear map. Now, is it clear what do I mean by bilinearity? It's just a generalization of the linearity. Okay, linearity, I mean the single argument you just generalize to two arguments. Multilinear means you have multiple arguments here, more than two, and you express them linearly. Okay, I hope it's clear. Now, okay, I have a vector space V and with basis EI. Okay, now I want to see how I can represent this in this basis. Okay, So this I can write as t tilde v. V is any vector in V. I can express that as a linear combination of ei. So let that linear combination be summation over I vi ei. Okay, comma w. You also express w in this basis. Its component will be something else, right? Some j wj ej, right? Where I and j are summed over. Now, because of this bilinearity, what is going to happen? Hmm? Because of the bilinearity, what is going to happen? If I know, suppose if I know, my aim is to calculate this, but if I know the action of t tilde on ei and ej, I know basically this, right? Answer for this because of the bilinearity. Okay, because what is going to happen? T tilde, this summation will be out, this j summation will be out, and then there will be vi wj. So this will be vi wj t tilde ei ej, right? Okay, so if I know this, okay, I know how to evaluate this. Okay, these are basically, this is basically ijth, this is the component of t tilde in basis, in this basis. Okay, you compare this with your vector, dual vector. What do you mean by dual vector? When it acts on vector, you get a number, right? Okay, now if I say that this is my basis in dual space, then this will give me delta ij. Given this, okay, given this thing, I can express any dual vector as a linear combination of this. And I know through this relation, I know what is V tilde acting on EJ, for example. What is its role? V tilde I can express as a linear combination of V tilde I can express as a linear combination of EI. Okay, this is my V tilde, and I am acting on EJ. What I am going to get? VI, okay, delta ij, summation over I. So this will be your VI. This is how you define your VI. Okay. So sorry, this should, there is no reason I should write this upper thing. Okay, so this should be VJ. Okay, so action of V tilde acting on EJ is to pick jth component of dual vector. Similarly, action of T tilde on EI is to pick ith component of whatever this may be, whatever this quantity may be. Okay. So if I know this, I know basically this. Is it clear? So these are called the component of T tilde in the basis, in this basis. Okay. Remember, there is an independent existence to this T tilde, irrespective of this basis. Okay. Fine. So maybe I think I should stop because it may. I wanted to do. I want to do something else now. Okay. I want to formalize this. This is just a rough draft of your tensors, tensor of rank 2, 0, tensor of rank 0, 2, and so on. Okay. In next class, we will formalize this in a proper manner. Okay. But what we need, the basic is your vector space, vector and dual vectors. Okay. If you understand that, then understanding the this general generalizing these vectors and dual vectors to higher ranks is easy. Generalization of these vectors and dual vectors will be easy if you understand vectors and dual vectors properly and their transformation rule. Okay. Any question regarding this? If not, then I will stop. Any question? Hello?
No, sir.
Okay. So I will stop. Maybe then we will meet on either on Tuesday or Wednesday directly. I think on Wednesday, because Tuesday also I will be occupied. Okay. So we will meet on Wednesday directly now. Okay. But please formalize this. Please read this. Okay. And be prepared for next class. Okay. If you have any difficulty regarding these vectors and dual vectors, please ask now, because I am not again going to repeat this. Okay. So in the textbook, you will see you will not see this. Okay, they will not start with these kind of things, vectors and dual vectors. Okay, they will directly start defining the tensor in the following way. Okay, they will say that the vector tensor of rank 20 are the objects which transform in such a way, and tensor of rank 02 are the objects which transform in way. Okay, but that should not be the definition of tensor, right? It should be intrinsic. Okay, it should not depend on transformation. Once we define what are co-vectors, contravariant vectors, or tensor of rank 2002, then how these objects will transform? That is the appropriate question to ask. But we should not define tensor in by saying that the tensors are the object which transform in way. That should not be the definition, right? Although that is correct, but that should not be used as definition. It is confusing. It then means that the tensor will depend on transformations, right? Okay. So once you understand the concept of vector, contravariant and covariant vector, their generalization is tensor of rank 20, tensor of rank 02, and so on. In general, we can have tensor of rank mn or tensor of type mn. M and n are integers. Okay, so we can have no mixed tensor also. Okay. Okay. Once you understand the difference between covariant vector and contravariant vector, be sure that whatever will follow from that, these generalizations, okay, will be easy. Okay, but for that you should understand the essential difference between contravariant vector and covector. Okay. I will come back to contravariant and covector. There is one more thing which I need to tell. What happens if I define inner product on this vector space? We have not introduced yet inner product. Okay, what happens if I introduce inner product on this space? Okay, fine. In the next class, we'll first generalize this concept of vectors and dual vectors. to tensors, and then we'll come back to co and contravariant vectors in slightly different way. Okay, fine. So I'll stop here. Okay. If you have any question, you can ask.